The U.S. Space Agency says its Parker Solar Probe has survived the closest ever approach to the Sun and is still continuing its mission.
1, 0.
NASA's Parker Solar Probe is no stranger to pushing boundaries, but its latest discovery has scientists locked in. For the first time, humanity has gotten this close to the Sun's mysterious surface.
I'm really excited to pass this off to the mission operations team and see all the science data that comes down and just get to enjoy.
And what the probe uncovered has stunned researchers worldwide. From unexpected solar winds to strange new phenomena in the Sun's corona, this mission could change everything we thought we knew about our star, the center of our universe. The Sun, our solar system's blazing plasma sphere, has captured human fascination for thousands of years. Ancient civilizations saw it as a life-giving force, essential for survival and worship. Over time, as science advanced, people worked hard to understand its influence, which touches everything from weather to navigation. Even with all we've learned, many aspects of the Sun remain a mystery, especially in its outer layers and the space around it. NASA's Parker Solar Probe represents a major leap forward in our effort to uncover the Sun's secrets. Launched in 2018, this mission is humanity's first attempt to physically reach the Sun's outer atmosphere. It's named after Dr. Eugene Parker, the scientist who first proposed the existence of solar wind in 1958. Unlike earlier spacecraft that stayed far away, Parker flies directly into the Sun's corona, enduring extreme heat and radiation to gather groundbreaking data. This mission builds on years of planning and technological progress. Studying the Sun's corona and solar wind is essential because they directly affect Earth and the solar system. The corona, the Sun's outermost layer, is puzzling because it's far hotter than its surface, a contradiction that defies basic physics. Understanding this heating mystery and the solar wind's role in phenomena like solar flares is vital. These solar events can disrupt communication systems, satellites, and power grids here on Earth. By gathering this data, Parker helps scientists predict and better prepare for such events. The mission goes beyond solving specific puzzles about the Sun. It impacts how we understand stars in general and the environments they create. By getting an up-close view of the Sun, scientists can refine models of stellar behavior that apply to stars across the galaxy. Parker's discoveries also help us understand how stars influence their surrounding planets, providing perspective on our place in the universe. The Parker Solar Probe shows the determination and ingenuity behind humanity's drive to explore. Its journey reminds us how far we can go when we work together and push boundaries. By diving into the Sun's atmosphere, Parker isn't just gathering data. It's changing how we see our star and its influence across the cosmos, bridging the gap. The journey to develop the Parker Solar Probe didn't happen overnight. It's rooted in decades of solar research and the limitations faced by earlier missions. Scientists have long recognized the importance of studying the Sun, but getting close enough to truly understand it has always been a major challenge. Before Parker, missions like Helios and Ulysses offered valuable data about the Sun's environment. Yet they remained far from the Sun's most intriguing regions, particularly the corona. These missions laid the groundwork, but couldn't answer some of the most important questions, like why the corona is so much hotter than the surface, or how the solar wind accelerates to such high speeds. Helios, launched in the 1970s, came closer to the Sun than any spacecraft before it, providing insight into the solar wind and interplanetary magnetic fields. Similarly, Ulysses, which launched in the early 1990s, revolutionized our understanding of the Sun's poles by studying them for the first time. However, even these remarkable efforts couldn't penetrate the Sun's outer atmosphere. Distance limited what they could observe and measure, leaving critical gaps in our understanding of solar phenomena. As scientists processed this wealth of data, the need for a more daring mission became clear. The vision for what would become the Parker Solar Probe began to take shape as early as the 1950s. For decades, researchers dreamed of a mission capable of withstanding the intense heat and radiation required to reach the corona. Yet the necessary technology simply didn't exist. Building a spacecraft that could fly so close to the Sun wasn't just about assembling advanced instruments. It demanded materials capable of enduring unimaginable temperatures and conditions while keeping the spacecraft's equipment intact. Advances in science and engineering eventually made it possible to turn this vision into reality. NASA officially announced the Solar Probe Plus mission in 2008, later renamed the Parker Solar Probe. The mission's primary goals were clear from the start: get closer to the Sun than ever before, collect detailed data on the corona's structure and dynamics, and solve long-standing mysteries like the coronal heating problem and the origins of the solar wind. Scientists hoped this mission would answer key questions about the Sun and its impact on the solar system. Another significant aspect of the mission was its name. NASA chose to honor Dr. Eugene Parker, a physicist whose work reshaped our understanding of the Sun. Dr. Parker was the first to theorize the existence of the solar wind, a stream of charged particles continuously flowing from the Sun. His groundbreaking work in 1958 wasn't universally accepted at the time, but subsequent observations proved his ideas correct. By naming the mission after him, NASA recognized his immense contributions to heliophysics. It was a rare honor, as NASA doesn't typically name missions after living people. Dr. Parker, who lived to see the probe's launch in 2018, described it as one of the highlights of his career. Beyond honoring Dr. Parker, the naming underscores the broader scientific legacy of those who've contributed to our understanding of the Sun. The mission's very existence symbolizes a culmination of efforts by generations of researchers, engineers, and visionaries who refused to let technological or scientific limitations stop them. At its core, the Parker Solar Probe represents humanity's boldest attempt to explore our closest star. The mission wouldn't have been possible without the technological breakthroughs that preceded it, from heat-resistant materials to advanced guidance systems capable of handling the extreme demands of solar exploration. By getting closer to the Sun than any previous spacecraft, Parker allows scientists to study its mysteries with unprecedented precision, fulfilling a dream that had been out of reach for so long. The genesis of the Parker Solar Probe demonstrates how far we've come in our pursuit of knowledge. It's not just about collecting data. It's about overcoming challenges that seemed insurmountable just a few decades ago, and it wasn't easy. Designing a probe to touch the Sun, designing a spacecraft to touch the Sun, demanded an unprecedented level of engineering. The Parker Solar Probe needed to handle heat and radiation far beyond what any previous mission had encountered. Its creation involved a blend of cutting-edge materials, innovative systems, and years of research. Every detail of its design reflects the unique challenges of traveling into the Sun's atmosphere while ensuring that critical data is gathered and relayed back to Earth. The Parker Solar Probe's structure is a masterclass in resilience. Engineers designed it to survive the intense radiation and gravitational forces near the Sun. At its closest approach, the spacecraft speeds through space at about 430,000 miles per hour, making it the fastest human-made object in history. To withstand the Sun's pull and maintain structural integrity under such immense velocity and heat, the spacecraft had to be lightweight yet incredibly durable. The materials used include advanced carbon composites and metals that can resist thermal expansion and distortion. The probe's size was another critical factor. It measures just under 10 feet tall and weighs about 1,500 pounds. This compact design minimizes the surface area exposed to direct sunlight while maximizing efficiency. Its solar panels retract partially during the closest approaches to the Sun, ensuring only what's necessary is exposed while keeping the internal systems powered. One of the probe's most essential components is its heat shield, officially called the Thermal Protection System. This 8-foot diameter shield is made of carbon composite materials, which can withstand temperatures of nearly 2,500 degrees Fahrenheit on the sun-facing side, while keeping the internal instruments at a comfortable room temperature. The heat shield's revolutionary design uses 2 panels of reinforced carbon-carbon sandwiching, a lightweight foam core. Despite its immense strength, it remains lightweight, a crucial factor for the probe's launch and operation. The TPS doesn't just block heat, it also deflects intense radiation. This ensures the spacecraft's internal components and instruments aren't damaged, allowing them to operate smoothly. The heat shield maintains its effectiveness across Parker's 7-year mission, proving how crucial thermal engineering is for exploring extreme environments. Given its close proximity to the Sun and high speeds, Parker Solar Probe couldn't rely on constant human guidance. The spacecraft operates with highly advanced autonomous systems to navigate and adapt to the challenging solar environment. These systems detect and correct its position automatically, ensuring the heat shield stays aligned with the Sun to protect vulnerable components. The probe also has an autonomous cooling system for its solar arrays. Without this, the arrays would overheat and stop providing power. The cooling system uses a water-based loop that dissipates excess heat, a design that works reliably even in space's harsh conditions. Realignment protocols are another key feature. If Parker strays even slightly from its optimal orientation, its onboard systems trigger immediate corrections, ensuring the mission remains on track. This level of automation is necessary, given that communication delays with Earth can take up to several minutes. In such extreme conditions, even a small mistake could jeopardize the entire mission. At the heart of the Parker Solar Probe's mission are its scientific instruments, designed to collect data about the Sun's magnetic fields, plasma, and energetic particles. The probe carries 4 primary instrument suites. Fields measures electric and magnetic fields to study the Sun's energy transfer processes. WISPR, the wide-field imager for Parker Solar Probe, captures visible light images of the solar corona and solar wind structures. SWEP, solar wind electrons, alphas and protons, collects data on solar wind particles to analyze their speed, density, and temperature. ISHIS, integrated science investigation of the Sun, detects high-energy particles emitted during solar storms. Each instrument suite is mounted and calibrated with precision to withstand extreme conditions while gathering accurate and comprehensive data. Together, they enable scientists to solve long-standing solar mysteries like the corona's heating and the acceleration of solar wind particles. The Parker Solar Probe represents the pinnacle of engineering for space exploration. Its robust design, groundbreaking heat shield, and autonomous systems all work together to ensure the mission's success in the most hostile environment humanity has ever studied. Packed with cutting-edge scientific tools, the probe pushes the boundaries of what technology can achieve, providing us with invaluable insights into the star that sustains life on Earth. This combination of innovation and determination is what makes Parker Solar Probe a marvel of modern engineering. Building the perfect probe was the first step. The mission had to be planned perfectly for things to progress the way they were supposed to. Mission timeline. The Parker Solar Probe's mission timeline is a carefully orchestrated sequence designed to bring it closer to the Sun than any spacecraft in history. It showcases how ingenuity and precise planning can overcome challenges that seemed insurmountable just decades ago. On August 12, 2018, NASA launched the Parker Solar Probe from Cape Canaveral aboard a Delta IV Heavy rocket, one of the most powerful rockets available. The choice of this launch vehicle was critical. The probe required immense velocity to escape Earth's gravity and head toward the Sun. Achieving the correct trajectory to intercept our star demanded precise calculations, given the intense gravitational forces and orbital dynamics involved. The mission's initial trajectory sent the probe toward Venus, laying the groundwork for a series of flybys designed to adjust its orbit. Each step represented the start of a journey aimed at transforming our understanding of solar physics. Venus flybys are a key strategy in Parker's mission, offering efficient adjustments to its orbit without excessive fuel consumption. Over the course of its mission, the probe will perform 7 Venus flybys, with the first taking place on October 3, 2018, less than 2 months after launch. Each flyby uses Venus's gravity to reduce Parker's orbital energy, enabling it to fall closer to the Sun with each pass. These gravity assists aren't just course corrections, they're transformative events, allowing the spacecraft to gradually spiral inward. Without Venus's gravitational boosts, achieving such proximity to the Sun would have been technically and financially impossible. The precision of these maneuvers is staggering. Each flyby demands exact timing and positioning to achieve the desired trajectory adjustments, ensuring that subsequent perihelion passes, the closest points to the Sun, bring the probe closer to its target. Parker's journey to the Sun involves 24 progressively closer perihelion passes over 7 years. With each pass, the spacecraft ventures deeper into the Sun's outer atmosphere, or corona, while also enduring increasingly hostile conditions. The first perihelion occurred on November 5, 2018, bringing the probe within 15 million miles of the Sun. As the mission progresses, the perihelion distance decreases incrementally. By 2024, during its final planned approach, Parker will come within 3.83 million miles of the Sun's surface, closer than any spacecraft has ever been. These repeated passes provide scientists with ongoing opportunities to collect new data, ensuring a steady stream of insights about the Sun's magnetic fields, solar wind, and corona. The methodical progression also allows engineers to monitor how Parker's systems handle the increasing intensity of the Sun's heat and radiation. The Parker Solar Probe has shattered multiple records since its launch. During its initial approaches, it broke the records for human-made object and closest approach to the Sun, achievements that it has continually surpassed. By its 7th perihelion in June 2021, it reached speeds of over 330,000 miles per hour relative to the Sun. The spacecraft's speed will ultimately exceed 430,000 miles per hour, fast enough to travel from New York to Tokyo in under a minute. This incredible velocity is not just a technical achievement. It's necessary to counteract the immense gravitational pull of the Sun. Each close approach provides unprecedented data about phenomena like coronal heating and solar wind acceleration. Before Parker, scientists could only observe these phenomena indirect or through theoretical models. Now, with the probe flying directly through these regions, they have direct measurements to validate and refine their understanding. Every milestone in Parker's mission builds on the last. From the initial launch to its intricate Venus flybys and record-setting perihelion passes, the probe is steadily delivering on its promise to revolutionize solar science. Its success is a testament to decades of planning, engineering, and scientific curiosity. By the mission's conclusion, Parker Solar Probe will have provided invaluable data, answering some of the most critical questions about the Sun, and it's already done a lot. Scientific discoveries and insights. The Parker Solar Probe's scientific discoveries represent groundbreaking advancements in our understanding of the Sun and the processes that shape our solar system. As the spacecraft ventures closer to the Sun than any probe before it, it has been gathering data that is transforming theories, solving long-standing mysteries, and revealing unexpected phenomena. One of the most baffling solar mysteries has been the coronal heating problem, why the Sun's corona is exponentially hotter than its surface. The corona reaches temperatures of 3 million degrees Kelvin, while the surface remains relatively cool at around 6,000 degrees Kelvin. Data from Parker Solar Probe has provided direct evidence of localized energy bursts and intense magnetic activity within the corona. These findings suggest that small-scale magnetic reconnection events and plasma turbulence contribute to heating. Moreover, the probe observed switchbacks, or sudden reversals in magnetic field direction, which may play a key role in transporting energy from the Sun's interior outward. Although scientists are still piecing together a complete explanation, Parker's insights are narrowing down the possibilities. The solar wind, a stream of charged particles emanating from the Sun, influences the entire heliosphere and Earth's space weather. Until now, its exact origins and acceleration mechanisms were not fully understood. Parker has provided unprecedented observations of plasma outflows from coronal holes, regions where magnetic fields open outward. By flying through these areas, the spacecraft captured data on particle acceleration and density fluctuations, allowing scientists to pinpoint how the solar wind gains its high velocities. Parker also revealed intricate details about the structure of solar windbursts, which appear more chaotic and dynamic than previously assumed. These findings are critical for understanding how solar wind impacts Earth's magnetosphere and for improving our ability to forecast space weather events like geomagnetic storms, which can disrupt satellites and power grids. Magnetic reconnection occurs when magnetic field lines in plasma break and reconnect, releasing vast amounts of energy. This process is pivotal in driving phenomena such as solar flares and coronal mass ejections, which can have significant effects on Earth. Parker Solar Probe has captured direct evidence of localized reconnection events in the solar atmosphere. These occurrences provide insights into how energy is transferred within the Sun's magnetic field and why its magnetic environment is so turbulent. These findings are a step toward understanding the behavior of magnetic fields throughout the universe, from stellar atmospheres to distant galaxies. Parker's data is helping scientists refine their models of magnetic reconnection and its implications across cosmic scales. The probe has offered fresh perspectives on Alfvén waves, oscillations in magnetic fields, and plasma that play a role in transferring energy within the solar atmosphere. Prior to Parker's observations, scientists theorized that Alfvén waves could help explain both coronal heating and solar wind acceleration. By flying through regions dominated by these waves, Parker provided the first direct measurements of their properties, such as frequency and amplitude. The probe also observed how Alfvén waves interact with the turbulent solar environment. This data is refining our understanding of how energy flows from the Sun's core to its outer layers and into space. In addition to its solar discoveries, Parker Solar Probe has contributed to planetary science, particularly regarding Venus. During its flybys, the spacecraft unexpectedly detected a dust ring orbiting Venus, composed of particles left behind by comets and other celestial objects. This discovery provides insights into how planetary dust rings form and persist, offering a window into the interactions between solar and planetary environments. It could also shed light on how such rings influence the atmospheres and surface conditions of planets. While the focus of the mission remains the Sun, these incidental observations underline Parker's wide-ranging scientific value. The Parker Solar Probe has already exceeded expectations, delivering data that is reshaping our understanding of the Sun and its influence on the solar system. From addressing century-old questions like the coronal heating problem to uncovering unexpected details about Venus, Parker's findings continue to inspire new theories and refine existing models. Although it would be naive to think that all of this happened without a hitch. Technological challenges and miles per hour. Designing and operating a spacecraft that ventures closer to the Sun than any before it required engineering ingenuity. The Parker Solar Probe faced monumental challenges, from navigating extreme temperatures to managing communication hurdles, all while ensuring mission-critical functionality. These technological achievements not only enabled groundbreaking discoveries, but also set new standards for space exploration. One of the mission's most daunting challenges was building a spacecraft that could survive the Sun's immense heat. At perihelion, the Parker Solar Probe endures temperatures exceeding 2,500 degrees Fahrenheit. Despite these harsh conditions, the instruments on board must remain operational and precise. The solution lies in the thermal protection system, an 8-foot-wide heat shield made from carbon composite materials. This shield reflects most of the Sun's energy while insulating the critical systems behind it, keeping internal components at a relatively safe 85 degrees Fahrenheit. Additionally, the spacecraft's design minimizes its exposure by orienting itself so that only the thermal protection system faces the Sun. Real-world validation of the heat shield's performance came during Parker's first close approaches. The system successfully endured the extreme heat and proved its resilience. Operating so close to the Sun also brings a unique challenge: communication blackouts. During perihelion passes, the Sun's intense radiation disrupts direct signals between Parker and Earth. For extended periods, the probe must operate autonomously without real-time guidance from mission control. To address this, the Parker Solar Probe relies on pre-programmed sequences for conducting its tasks during blackouts. Engineers meticulously planned these operations in advance, accounting for every possible scenario the spacecraft might encounter. Once Parker emerges from the communication shadow, it uploads its stored data to Earth. This process involves delicate data compression protocols to ensure that all critical information is retained. While communication delays add complexity, they underscore the mission's reliance on robust autonomy and careful planning, a feature essential for missions venturing far beyond Earth. The Sun's proximity exposes Parker Solar Probe to intense levels of solar radiation. This radiation could destroy onboard electronics or corrupt data without adequate shielding. Unlike Earth-orbiting satellites, which benefit from the planet's magnetic field, Parker operates in an environment where it's directly exposed to high-energy particles and plasma. Engineers tackled this issue by incorporating highly durable materials and specialized radiation-hardened electronics into the spacecraft's design. All critical components are housed behind the heat shield, further reducing their exposure to hazardous radiation. These efforts have ensured that the probe continues to function despite an environment more hostile than almost any spacecraft has encountered. Parker's ability to withstand such radiation has set a benchmark for future missions aiming to operate in similarly extreme conditions. Perhaps one of the most impressive aspects of the Parker Solar Probe is its autonomy. Traveling at speeds exceeding 430,000 miles per hour and navigating close to the Sun, the spacecraft must make rapid decisions on its own. For example, Parker relies on an advanced guidance and navigation system that keeps the heat shield perfectly aligned with the Sun, ensuring protection for onboard systems. It also employs a sophisticated cooling system to manage temperature fluctuations affecting its solar panels, extending their efficiency and longevity. Given the challenges of a solar mission, where immediate human intervention isn't possible, Parker's autonomy is critical. It can detect and correct anomalies, adjust its trajectory, and manage energy consumption, all without waiting for commands from Earth. This technological leap demonstrates how autonomous systems will be indispensable for future deep space missions. The findings from the mission have already taught us a lot. Parker Solar Probe's contribution. The discoveries from Parker provide critical insights into how solar phenomena impact the magnetosphere, technology on Earth, and astronauts in space. By expanding our understanding of solar activity, this mission has the potential to influence space weather prediction and the development of protection measures across multiple domains. The Sun emits a constant stream of charged particles, collectively known as the solar wind, which shapes the environment around Earth. This stream interacts with the planet's magnetosphere, the magnetic bubble that shields Earth from harmful solar radiation. While this interaction can create captivating auroras, it also causes more harmful effects, such as geomagnetic storms and solar energetic particle events. Parker Solar Probe's proximity to the Sun allows it to observe and measure solar wind and magnetic fields closer than any previous mission. This provides scientists with much-needed data on how magnetic fields are generated within the corona and how solar wind accelerates to speeds that can influence space weather on Earth. By directly monitoring solar conditions that drive magnetosphere dynamics, Parker delivers a clearer picture of the Sun's behavior, helping us understand how these charged particles affect Earth's protective shield. Through these insights, scientists hope to model geomagnetic storms with greater precision. Understanding the exact conditions in which these storms form provides key data on their potential intensity and timing. This knowledge allows for a more accurate prediction of how space weather events affect Earth's atmosphere, including communication and satellite systems. Solar storms, driven by intense solar flare activity, can cause widespread technological disruptions on Earth. These events unleash high-energy particles and electromagnetic radiation that can damage satellites, disrupt GPS systems, and interfere with power grids. However, the true impact of these storms varies based on their intensity and timing, factors that are challenging to predict. Parker's observations are improving our ability to forecast solar storms. By analyzing solar wind behavior near the source, directly in the solar corona, Parker is helping scientists identify early warning signals that can predict when and where solar storms will most likely occur. As it collects magnetic data from this region, the probe provides more details on the driving forces behind solar events, such as coronal mass ejections and solar flares. This deeper understanding enhances space weather models, allowing for more accurate forecasting of solar activity. As solar storms are tracked more efficiently, space weather services can issue warnings well in advance. Such forecasts give industries, governments, and critical infrastructure companies more time to protect satellite assets and adjust communication systems, preventing or minimizing disruptions. As humanity's presence expands beyond Earth, protecting astronauts from solar radiation becomes a high priority. Solar storms and high-energy cosmic rays pose serious health risks to astronauts, as prolonged exposure can damage tissues and increase the risk of cancer. Solar radiation is also hazardous to the electronics onboard spacecraft, where it can interfere with systems, causing malfunctions and even complete failure. Parker Solar Probe is contributing to the protection of astronauts and space assets by improving our understanding of solar radiation. By observing and characterizing radiation patterns closer to the Sun than any previous spacecraft, it is providing essential data on how solar particle events behave. This data will allow for a more comprehensive radiation risk model for space missions, helping to predict when solar events will be strong enough to affect astronaut health or spacecraft operations. The real-time observations collected by Parker also lead to better space weather forecasting for manned missions. In combination with data from other satellites and space stations, the information from Parker will ensure that astronauts in deep space or lunar bases receive advanced warning when dangerous solar conditions approach. Having a more accurate prediction of solar flare intensity or coronal mass ejections could allow for mission adjustments to keep astronauts safe from potential harm during spacewalks or other activities exposed to space radiation. Additionally, with NASA planning for missions to the Moon and Mars, an in-depth understanding of space weather is crucial for ensuring crew safety. Parker's findings on solar phenomena, along with future follow-up missions, can be instrumental in creating advanced protective measures for astronauts, such as radiation-shielded habitats or real-time avoidance strategies. The data Parker Solar Probe continues to send back to Earth will help solve many fundamental questions about solar activity and its far-reaching effects. These findings enhance space weather prediction and add critical pieces to the puzzle of understanding how solar winds and magnetic fields work. From understanding geomagnetic storms to developing solutions to safeguard space technology and astronauts, the mission is shaping the future of how we manage our relationship with the Sun. In the years to come, as our reliance on space technology grows, particularly in telecommunications, weather prediction, and space exploration, understanding and predicting space weather will become increasingly important. With Parker Solar Probe providing the data needed for these advancements, its contributions will continue to influence and refine efforts to safeguard life and infrastructure on Earth and beyond. What do you think? Leave your thoughts in the comments below. And if you liked this video, don't forget to subscribe to our channel. See you in the next one.